Have you ever stopped to think about the atoms that make up your body, where they came from, and how they ended up in you? It might sound like something out of science fiction, but the truth is that nearly every particle within you has traveled across the cosmos. They were created in ancient stars, shaped by cosmic explosions, and delivered to Earth by processes that span billions of years. Let's dive into how we are, quite literally, made of stardust. The story of our particles begins 13.8 billion years ago, at the moment of the Big Bang. When the universe first exploded into existence, it was an unimaginably hot and dense soup of energy. As the universe expanded and cooled, this energy condensed into the simplest of elements, hydrogen and helium. Together, these two made up about 99% of the universe's composition in its earliest moments. At this stage, the universe was still lifeless in the sense that the heavier elements like carbon, oxygen, and nitrogen, which are essential to life, did not yet exist. It would take the formation of the first stars to begin the alchemy that creates these heavier elements. Stars are often described as nuclear furnaces, and for good reason. Deep within their cores, the intense pressure and heat fuse hydrogen atoms into helium, a process called nuclear fusion. This fusion releases enormous amounts of energy, which is why stars shine so brightly. But fusion doesn't stop at helium. As stars grow older, they begin fusing helium into heavier elements like carbon and oxygen. Larger stars can go even further, producing neon, silicon, and eventually iron through a chain of increasingly complex fusion reactions. Fun fact: a star like our Sun can produce elements up to oxygen and carbon, but only massive stars, those more than 8 times the Sun's mass, can create iron and heavier elements. However, there's a limit to what a star can create through fusion. Once iron is formed in a star's core, fusion can no longer release energy. It becomes an energy sink. At this point, the star's life is essentially over. When a star runs out of fuel, it can no longer resist the inward pull of its own gravity. What happens next depends on the size of the star. For Sun-like stars, these stars shed their outer layers gently, creating beautiful planetary nebulae. The remaining core becomes a white dwarf, a dense, Earth-sized remnant that will slowly fade over billions of years. For massive stars, these stars end their lives in spectacular fashion. When their cores collapse, they explode in a supernova, releasing an incredible amount of energy, enough to briefly outshine an entire galaxy. It's during these explosive deaths that the heaviest elements, such as gold, uranium, and iodine, are created through a process called rapid neutron capture, or the R process. These elements are flung into space along with all the other elements the star created during its life. Fun fact: the gold in your wedding ring or smartphone likely came from a neutron star collision or a supernova that occurred billions of years ago. Once these elements are ejected into space, they don't just float around aimlessly. They become part of vast clouds of gas and dust known as nebulae. Over time, gravity causes these clouds to collapse and condense, forming new stars, planets, and even solar systems. Our solar system, including Earth, formed about 4.6 billion years ago from such a cloud. This nebula was enriched by the stardust of previous generations of stars, meaning that every atom in the rocks, oceans, and living beings on Earth has a stellar origin. Let's take a closer look at the human body to see how much of it comes from stardust. Remarkably, about 93% of your body mass is made up of just 3 elements: oxygen, carbon, and hydrogen. Here's how they and other key elements in your body connect back to the stars. Oxygen, which makes up 65% of your body mass, was formed in stars slightly larger than the Sun through helium fusion. Carbon, making up 18%, was created in massive stars through the triple alpha process, which is the fusion of 3 helium nuclei. Hydrogen, accounting for 10%, is the most ancient element, created directly after the Big Bang. Calcium, which is 1.5%, was made in supernova and is vital for bones and teeth. Lastly, iron, making up 0.006%, was produced in the core of massive stars and distributed during supernovae. The phrase "we are made of stardust" was popularized by astrophysicist Carl Sagan, and it beautifully encapsulates the connection between humanity and the cosmos. Scientifically, it reminds us of the recycling process that occurs on a cosmic scale. Philosophically, it underscores how deeply intertwined we are with the universe. Consider this. Every breath you take contains oxygen atoms forged in a star billions of years ago. The iron in your blood comes from the remnants of a massive star's violent death. Even the water you drink contains hydrogen that dates back to the birth of the universe itself. Realizing that we are made of stardust changes how we view ourselves. We're not separate from the universe. We are its children, built from the same particles that light up the stars. This perspective also raises profound questions. If we are stardust, how many other planets or organisms share our elemental origins? Could stardust particles that were once part of ancient stars now be part of new forms of life elsewhere in the universe? The journey of particles from the cores of ancient stars to the cells of living organisms is one of the most incredible stories ever told. It bridges astronomy, physics, and biology, showing us how interconnected everything in the universe truly is. In the next segment, we'll explore the life cycles of stars in greater detail, diving into the processes that create the building blocks of life. Don't forget to like, subscribe, and hit the notification bell to continue this cosmic adventure with Infinitia Verity. In the previous segment, we explored how stars are the birthplace of the elements that make up everything around us, including our own bodies. Now let's take a deep dive into the life cycle of stars, uncovering how these cosmic alchemists create the building blocks of life and spread them across the universe. The birth of a star. From dust to luminosity. Every star begins its life as part of a nebula, a vast cloud of gas and dust. These clouds are the remnants of earlier stellar deaths, enriched with heavy elements like carbon, oxygen, and iron. Over time, gravity causes these particles to clump together, forming a protostar, a dense, hot core surrounded by a disk of gas and dust. As the protostar grows in mass, its internal pressure and temperature rise. When the core temperature reaches around 10 million degrees Celsius, hydrogen nuclei begin to fuse into helium, releasing vast amounts of energy. This marks the birth of a fully fledged star, a process that can take millions of years. Main sequence stars, the Cosmic Workhorses. Once nuclear fusion begins, a star enters the main sequence phase, the longest and most stable period of its life. During this time, the outward pressure from fusion balances the inward pull of gravity, creating a stable, shining star. Small stars, like red dwarfs, burn their fuel slowly and can last tens of billions of years. Medium stars, like our Sun, burn hydrogen into helium for around 10 billion years before evolving further. Massive stars, on the other hand, burn through their fuel in just a few million years due to their enormous energy output. Stars on the main sequence are fusion factories, producing elements up to helium, carbon, and oxygen. Their size determines how much heavier they can go before collapsing. The death of stars, elemental dispersal. As stars exhaust their hydrogen fuel, they leave the main sequence and enter their final stages of life. The manner in which a star dies depends entirely on its mass. 1. Sun-like stars, planetary nebulae, and white dwarfs. When a star like the Sun runs out of fuel, its core contracts while its outer layers expand, creating a red giant. Eventually, the outer layers are ejected, forming a planetary nebula, a stunning, glowing shell of gas. The core becomes a white dwarf, a dense, Earth-sized remnant that gradually cools over billions of years. 2. Massive stars, supernovae, and black holes. Massive stars meet a far more dramatic end. After exhausting their fuel, they collapse under their own gravity, causing a massive explosion called a supernova. This explosion creates new elements, from silicon to gold, and disperses them across the galaxy. If the star's core is between 1.4 and 3 solar masses, it becomes a neutron star. If it's larger, it collapses further to form a black hole, where gravity is so intense that not even light can escape. The remnants of dying stars enrich the interstellar medium, providing the raw materials for new stars and planets. This cosmic recycling ensures that the heavy elements created in one generation of stars become the seeds for the next. For example, carbon and oxygen from a dying star might become part of a future planet's atmosphere. Iron from a supernova could eventually form the core of a rocky planet like Earth. This process is why our solar system is so rich in elements essential for life. Without generations of star formation and death, Earth would be nothing more than a barren rock. Every element necessary for life, carbon for organic molecules, oxygen for respiration, iron for blood, and calcium for bones, was created in stars. This makes stars not just cosmic alchemists, but also the architects of life itself. Fun fact: it's estimated that the Milky Way experiences one supernova every 50 years, ensuring a steady supply of stardust. Another fun fact: some of the heaviest elements, like gold and platinum, are thought to originate from neutron star collisions, not just supernovae. The life cycle of stars shows us the universe's capacity for creation and transformation. Through their births, lives, and deaths, stars forge the elements that make life possible and scatter them far and wide, ensuring that even in death, they contribute to new beginnings. From humble beginnings in a nebula to dramatic ends as supernovae or white dwarfs, stars shape the universe in profound ways. Their cycles of life and death are the reason we exist today, a testament to the interconnectedness of all matter in the cosmos. In the next segment, we'll focus on one of the most dramatic events in a star's life, the supernova explosion. We'll explore how these cosmic fireworks contribute to the creation of elements and the dynamics of the universe. Stay tuned and don't forget to like, share, and subscribe to Infinitia Verity. In the life cycle of stars, there is no event as dramatic or significant as a supernova. These cosmic explosions mark the violent deaths of massive stars and are responsible for creating many of the heavy elements that form planets, structures, and life. In this segment, we'll delve into the science behind supernovae, their types, and their impact on the universe. A supernova occurs when a star undergoes a sudden, catastrophic explosion, releasing an immense amount of energy in a fraction of a second. To put it in perspective, a single supernova can outshine an entire galaxy and release as much energy in that moment as our Sun will over its 10 billion-year lifetime. Supernovae play a vital role in the universe by dispersing heavy elements formed in the star's core into the surrounding space. These elements, including iron, calcium, and even gold, are the building blocks of new stars, planets, and ultimately life. There are two main types of supernovae, each with its own unique origin story. Type 1 supernovae. These occur in binary star systems where one star is a white dwarf. The white dwarf pulls material from its companion star until it exceeds the Chandrasekhar limit, which is about 1.4 times the mass of the Sun. This triggers a thermonuclear explosion, obliterating the white dwarf and scattering elements like carbon and oxygen. Type 2 supernovae. These happen when massive stars, 8 or more times the Sun's mass, exhaust their nuclear fuel. Without energy from fusion, the core collapses under its own gravity. The outer layers rebound off the core in a massive explosion, creating elements heavier than iron. Supernovae are critical for the formation of elements heavier than iron, such as gold, platinum, and uranium. These elements are created through a process called rapid neutron capture, or the R process. In the intense heat and pressure of a supernova, neutrons are added to atomic nuclei faster than they can decay, creating heavy, stable elements. Without supernovae, many of the materials we take for granted, like gold in jewelry or uranium in nuclear reactors, wouldn't exist. The energy released during a supernova is staggering. When the famous SN 1987A supernova exploded in the Large Magellanic Cloud, it released energy equivalent to 10 octillion nuclear bombs. This explosion illuminated its neighboring galaxy and allowed astronomers to directly observe the physics of a supernova for the first time. Supernovae don't just create elements, they also shape the universe on a large scale. The explosion sends shockwaves through space, compressing nearby gas clouds and triggering the formation of new stars. The expelled materials mix with interstellar gas, seeding future generations of stars and planets with the elements needed for life. Without supernovae, the universe would lack the diversity of elements needed to form complex structures. Supernovae are beautiful and essential for the universe, but they are not entirely harmless. If a supernova were to explode within 50 light-years of Earth, the intense radiation could destroy our planet's ozone layer, exposing life to deadly UV rays. One potential culprit is Betelgeuse, a red supergiant in the Orion constellation. It's nearing the end of its life and could go supernova within the next 100,000 years. When it does, it will be so bright that it will outshine the full moon in our night sky. Fun fact: despite its brightness, Betelgeuse's explosion won't harm Earth because it's 640 light-years away, far enough to admire without fear. Humanity has witnessed several supernovae over the centuries, often recording them as mysterious celestial phenomena. SN 1054, observed by Chinese and Arab astronomers, created the Crab Nebula. It was so bright that it was visible during the day for weeks. SN 1604, also known as Kepler's supernova, was documented by Johannes Kepler and was the last supernova observed in the Milky Way. These historical observations were crucial in advancing our understanding of the cosmos. Supernovae are the ultimate cosmic recyclers, ensuring that the elements created in stars are returned to the universe. Every atom of iron in your blood and calcium in your bones once resided in a massive star. When we marvel at the periodic table, we're looking at the legacy of countless stellar explosions. Fun fact: scientists estimate that the human body contains about 0.2 milligrams of gold, created during a supernova or neutron star collision billions of years ago. Modern telescopes like the James Webb Space Telescope and facilities like the Vera Rubin Observatory are unlocking new insights into supernovae. By studying their light and remnants, astronomers are piecing together the history of the universe and its chemical evolution. For example, Webb recently captured the remnants of Cassiopeia A, a supernova that exploded 11,000 years ago, revealing new details about how these events distribute elements into space. Supernovae are among the most powerful and transformative events in the universe. They not only mark the end of a star's life but also sow the seeds for new stars, planets, and even life itself. Without them, the universe would lack the rich variety of elements that make our existence possible. In the next segment, we'll explore another aspect of our stardust heritage, the role of neutron stars and black holes in cosmic evolution. Stay tuned, and don't forget to like, share, and subscribe to Infinitia Verity. Supernovae don't just create heavy elements, they also give birth to some of the most extreme objects in the universe: neutron stars and black holes. These remnants of stellar death push the boundaries of physics and play a vital role in cosmic evolution. In this segment, we'll uncover their secrets and their connection to the particles that make up life. When a massive star explodes as a supernova, its core may collapse into a neutron star. These are incredibly dense objects, packing more mass than the Sun into a sphere about 20 kilometers in diameter, roughly the size of a city. A teaspoon of neutron star material would weigh about 4 billion tons, or the equivalent of 100 Mount Everests. The gravity on a neutron star's surface is about 2 billion times stronger than Earth's. Neutron stars are formed when the collapsing core of a star becomes so dense that protons and electrons combine to form neutrons. This creates an object composed almost entirely of neutrons, held together by immense gravitational forces. They also rotate incredibly fast. Newly formed neutron stars, called pulsars, can spin hundreds of times per second, emitting beams of radiation from their magnetic poles. These beams sweep across space like cosmic lighthouses. Magnetars, neutron stars on steroids. A rare type of neutron star, known as a magnetar, has an extraordinarily strong magnetic field, up to a quadrillion or 1,000 trillion times stronger than Earth's. Magnetars can release bursts of energy so intense they could disrupt electronics on Earth from thousands of light-years away. Black holes, the universe's ultimate powerhouses. If the core of a collapsing star is massive enough, more than 3 times the mass of the Sun, it continues collapsing into a black hole. These are regions of space where gravity is so strong that nothing, not even light, can escape. What makes a black hole? At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics break down. Surrounding it is the event horizon, the boundary beyond which nothing can return. Black holes come in several types. 1. Stellar mass black holes, formed from supernovae. These are typically a few times the sun's mass. 2. Intermediate black holes. With masses ranging from hundreds to thousands of suns, these are rare and mysterious. 3. Supermassive black holes. Found at the centers of galaxies, these giants can have masses equivalent to billions of suns. Black holes aren't just cosmic vacuum cleaners. They play an active role in shaping galaxies and distributing matter across the universe. Their immense gravity pulls in gas and dust, forming accretion disks that emit powerful X-rays and other radiation. Jets of material can also be ejected from black holes, influencing star formation in their vicinity. Neutron stars and black holes are critical to the production and dispersal of heavy elements. For example, when two neutron stars collide, they produce a burst of heavy elements like gold, platinum, and uranium through the R process. The resulting explosion, called a kilonova, can release as much energy as a supernova. While these cosmic titans are far away, they do pose theoretical risks. Gamma-ray bursts. Magnetars or neutron star collisions can release gamma-ray bursts that could sterilize entire planets if they hit directly. Wandering black holes. Rogue black holes drifting through space could disrupt planetary systems, though the chances of one entering our solar system are incredibly slim. The scientific frontier studying neutron stars and black holes. Modern telescopes and gravitational wave detectors are revolutionizing our understanding of neutron stars and black holes. LIGO and Virgo. These facilities detect ripples in space-time caused by collisions involving black holes or neutron stars. James Webb Space Telescope observes the remnants of stellar explosions and the environments around black holes, shedding light on their role in cosmic evolution. The role of neutron stars and black holes in us. Ultimately, neutron stars and black holes contribute directly to the stardust that makes us. The heavy elements they create during collisions are incorporated into planets, organisms, and even technology. For example, the gold in your jewelry likely came from a neutron star collision billions of years ago. The iron in your blood was forged in the core of a massive star, which may have collapsed into a black hole. Closing thoughts for segment 4. Neutron stars and black holes are among the universe's most extreme phenomena. They're both destructive and creative forces, shaping galaxies, producing elements, and connecting us to the cosmos in profound ways. In the next segment, we'll explore how the particles created by these cosmic titans find their way into living organisms on Earth, completing the journey from stardust to life. In the previous segments, we explored how stars and their remnants create the elements that make life possible. But how do these particles, scattered across the cosmos, come together to form planets like Earth? In this segment, we'll journey through the process that transforms stardust into planetary systems and ultimately, the cradle of life. After supernovae eject their stardust into the universe, the material becomes part of nebulae, vast clouds of gas and dust. These nebulae are the breeding grounds for new stars and planetary systems. Over time, gravity causes denser regions of the nebula to collapse, forming a spinning protoplanetary disk around a central protostar. This disk contains all the raw materials, gas, dust, and elements like carbon, oxygen, and silicon, needed to build planets. As the protostar in the center of the disk begins to shine, particles in the surrounding disk start to collide and stick together, forming planetesimals, the building blocks of planets. These planetesimals grow larger through a process called accretion, eventually becoming protoplanets. Key stages in planet formation include 1. Dust to rocks. Tiny grains of dust, made of silicates and metals, collide and clump together to form larger particles. 2. Rocks to planetesimals. These particles grow into kilometer-sized bodies. 3. Planetesimals to planets. Gravity pulls planetesimals together to form protoplanets. The material in the disk segregates by temperature. Close to the star, only rocky materials like silicates and metals survive the heat, forming terrestrial planets like Earth. Farther out, Volatile compounds like water and methane remain solid, forming gas giants and icy worlds. Earth's formation, a story of stardust. Earth formed about 4.6 billion years ago in the inner part of the solar nebula, where temperatures were high. Here's a breakdown of the process. Core formation. Heavy elements like iron and nickel sank to the center, forming Earth's core. Mantle and crust lighter silicates formed the mantle and crust, creating the solid structure of our planet. Volatile delivery water and organic molecules, essential for life, were likely delivered by asteroids and comets, which carried stardust enriched with these materials. Earth's moon also has a stardust origin. It likely formed when a Mars-sized protoplanet called Theia collided with the young Earth. The debris from this impact coalesced into the moon. This event had profound effects on Earth's development. The moon stabilized Earth's tilt, creating stable seasons. Tidal forces from the moon influenced the development of ocean ecosystems. Once Earth formed, it went through several stages to become habitable. Early atmosphere volcanic activity released gases like carbon dioxide, water vapor, and nitrogen, creating a thick atmosphere. Oceans. As Earth cooled, water vapor condensed into liquid water, forming oceans. Organic molecules, complex organic molecules formed from carbon-rich stardust, began to accumulate in Earth's early oceans, setting the stage for life. The elements in Earth's crust, oceans, and atmosphere all originated in stars. Here's a breakdown of their stardust origins. Carbon and oxygen, crucial for organic molecules and water, formed in massive stars. Iron makes up Earth's core and much of its crust, created in supernovae. Silicon essential for rocks and minerals, produced in the later stages of stellar fusion. Even the rare elements we rely on for technology, like gold and platinum, come from neutron star collisions or supernovae. Earth isn't the only planet made of stardust. Planets in other solar systems likely form through the same processes, raising intriguing questions. Could stardust particles from other stars harbor the ingredients for life? Are there other Earth-like planets where stardust has led to the emergence of life? The study of exoplanets, planets orbiting stars beyond our Sun, suggests that the building blocks of life, like water and organic molecules, are common throughout the galaxy. Earth's journey doesn't end with its formation. In billions of years, when the Sun exhausts its fuel and becomes a red giant, it will engulf the inner planets, including Earth. The Sun will then shed its outer layers, creating a planetary nebula and enriching the interstellar medium with stardust. This material will become part of new nebulae, stars, and planetary systems, continuing the cosmic recycling process. Fun fact: in 5 billion years, the stardust from Earth might contribute to the formation of new planets, potentially seeding life in another part of the galaxy. The process of turning stardust into planets is a story of cosmic creativity and interconnectedness. Every element on Earth, from the rocks beneath our feet to the air we breathe, has a stellar origin. Understanding this connection gives us a profound sense of belonging in the universe. In the next segment, we'll zoom in even further to explore how the particles forged in stars came together to form the molecules that make life possible. Don't miss it, and remember to like, share, and subscribe to Infinitia Verity.